So we are now on simple circuit application. So we will not discuss for now higher order differential equations, which can also be having circuit applications. In our case, we will limit our discussion to RL and RC circuits. So we have resistor, inductor, and capacitors present in these circuits, but we will only be talking about them, or they will only be present in our circuit two at a time. So what do I mean with two at a time? You can have an RL circuit, so resistor, inductor, or you can have an RC circuit, resistor, and capacitor. Now, we will not discuss for now RLC circuits where all three will be present. Because if we have such, then we will be talking about a higher order differential equations, and we haven't yet started on techniques in evaluating such. So we will just limit for now our discussion on the two combinations of these three circuit elements. Okay, so you could see here in the document, and just enlarge, you can see in the document that the first of the three circuit elements that I will be discussing will be the resistor. We have this resistor, and it's one of the circuit elements that will be present in the circuits later on that you will be exposed to. And in this particular resistive circuit, in this case, you have current I, which is passing through this particular element. Now, there will be a corresponding voltage drop in association with the current passing through this resistive element. And that particular voltage drop is represented by the product of the resistance of your resistor in ohms and the current in amperes. So you have it here anyhow. So we write the ohms in this symbol and the current I, and its unit is in amperes. And of course, in terms of voltage, we have the V. So the product of Ri is our voltage drop across this resistor element. Now, another circuit element that will be present in our circuit also is the inductor. So you can see it in here, a different representation of your inductor. And if it's written in your circuit, it could be represented by this one. The current passing to our inductor is specifically represented by small letter I with the subscript capital letter N. And if we do have a voltage drop in our resistor represented by, again, Ri, in the case of our inductor, it's now the product of the inductance, L, inductance, which is, yes, L, represented as L, but the unit is in Henry or Henries. And you have the rate of change of the current with respect to time. So this time now you could see that the voltage drop across your inductor is containing a derivative. So once present in the element, in the circuit equation, wherein we're accounting for the summation of all voltage drops in our circuit, you will now have a differential equation because of the presence of this derivative. Okay, so this is how we represent the voltage drop across our inductor. Now, same thing, the V is still voltage in having the units in volts. Now, okay, so our current rate of change of the current is in amperes per unit time, or current per unit time. And our time, when you speak of circuits, is always expressed in terms of seconds. So if it's not expressed in seconds, just have it converted to seconds. Now, there's a note here, and it's very important that you have to note that when V sub L is equal to 0, your inductor acts like a short circuit. And this is when your IL is constant and your circuit is said to be a DC circuit. So meaning it's connected to a battery. So it's a DC circuit. So when is this? So in a DC circuit, V sub L is equal to 0. You may wonder why is V sub L equal to 0, or the voltage drop across your inductor is 0 when you have a DC circuit. It's because if we have a DC circuit, this rate of change of the current with respect to time is 0. Our current is constant when we have a DC circuit. So that is why, based on the formula here, for the voltage drop across your inductor, you will have the derivative of I with respect to time set to 0, and as such it follows that your voltage drop across your inductor will be 0 also. So this is the scenario when your circuit is a DC circuit and your VL acts like a short circuit. Okay? The last circuit element is the capacitor. So you have different illustrations here of the capacitor, and in the circuit when drawn, it's represented like this. Okay? We have voltage drop also across our capacitor, and we do account for it later also as well in our circuit. Now, when we speak of our capacitor, there is this new quantity, electrical quantity that is associated with it, and that is the charge in the capacitor. Okay, the charge in the capacitor is equal to the product of the capacitance having the unit farad and the voltage. Okay, so product of capacitance and volts giving you a charge in coulombs. Now, in this particular circuit, when we have a capacitor present, we also represent the current in form of a derivative. Just like in here, we represented this one. The current is in the derivative representation. In here, your current is represented in the form of a derivative, but not itself in their present, but rather it's now the rate of change of the charge in your capacitor per unit time. So I is dq dt. How will the charge in your capacitor change per unit time? So you can see here the rate of change of the charge. So charge being in coulombs, C, we divide it in time unit, which is in seconds. So the rate of change of the voltage in this case, the rate of change of the voltage in this case in our circuit is dV dt. So this time class, it is the current which is represented by a product of a constant quantity and a derivative. If in the inductance, we have the voltage drop across our inductor, which has the presence of the derivative, the rate of change of the current with respect to time. In the capacitor, it is the current itself which has a portion of it or a part of it represented by a derivative. So the current is your capacitance in farad multiplied to the rate of change of the voltage with respect to time. Okay, so when we set up our model D, anyway, it will be presented to you in a little while. It is now the current which will have the presence of the derivative. Now, there's another note here, just like what we have in the inductor, that if the current is 0, capacitor acts like an open circuit. So in here, yes, aton inductor, if the voltage drop across your inductor is 0, it is the inductor that acts like a short circuit. This one, it's not a short circuit, but this one is an open circuit. No current passes through your circuit elements if I is equal to 0. So it follows, I think it's common sense that you have an open circuit. And this is when your V is a constant voltage. So your voltage is not changing. So you could see here I is C dV dt. T, if it's dV dt, rate of change of the voltage with respect to time, and it is said here that voltage is a constant, so meaning this thing here will be 0. If dV dt will be 0 because it's not changing with respect to time, because it is said to be constant, then your I will be also 0 because C times 0 will be of course, a value which is nil or there's nothing to it, is 0. As to the circuits that have these elements, I said at the start of the discussion that we will only take them 2 at a time. So you have here on the left an RL circuit, and here on the right you have an RC circuit. Okay, and this is your power source. Okay, it could be an AC circuit, it could be a DC circuit. Now, before I proceed in here to the DEs that will model our circuit, whether we have this type of circuit rather, or this type of circuit, do you have any questions? Do you have any question as to anything here that I discussed so far? So if there is none, I assume and will presume that you have already taken this up in your physics, and this is not the first time that you have heard of this. So this is just but review. So no question in here. So limitation only is for these two circuits, RL and RC circuits. I think there's none, so I will proceed. Okay, let me just minimize. So the basic equation governing the current I in amperes in a simple KL circuit or RL circuit consisting of resistance R and an inductance L and an electromotive force E. So this is it's abbreviated as EMF in volts. This will be our DE. Okay, so let me just enlarge again. You can see the DE here, class, to be DI dt plus RI over L equal to E over L. This is for your RL circuit. So let me annotate. Right? This is for your RL circuit. This one. This is your model DE. So what does this imply, class? Whenever you're given a circuit which has a resistor and an inductor present there, this is automatically your differential equation. So in here you have your derivative of the rate of change of the current with respect to time. And you have here R over L times I, and you have here E over L. So R and L are constants. Okay, this is resistance, this is inductance. And your E can be a constant if you have a DC circuit. You have a battery as the power source, and this E can be a function of the sine or cosine if your circuit is an alternating current circuit, just like the one that we have at home and the one that we are using in school, and even industries are using this one. So most of the time, the E is not constant. It's an expression which has the sine or the cosine function. But nonetheless, whether we have an AC circuit or a DC circuit, this is our model DE. So whenever you start solving a problem consisting of a resistor and an inductor, you always start with the working equation. If there is a problem with the working equation regarding the quantities that are provided and the unknowns, that's the time that you find an alternative expression. Other than that, if there is no problem with the DE based on what you are provided and what is being asked, then you always at all times start with it. Okay, so this is your DE for an RL circuit. We also have a DE for the, let me just close this one here. We also have a DE for an RC circuit, and this is for the RC circuit. So we have here in this case a resistance and a capacitance, and also an EMF. No inductance in the equation because we want to limit our circuit to a first order differential equation, our circuit equation. So if we will have all three now, we will have a higher order DE, and we're not ready for it yet. Okay, so this is our model DE for an RC circuit. And the derivative, as you can see in here, is the rate of change of the charge in your capacitor with respect to time. And you have here the second term to be Q over RC, and you have here E over R on the right side. Same as what you have on the RL circuit model DE, you have the electromotive force in here. It could be a constant or it could be a function of the sine and cosine. Now, there is this very important relationship regarding the Q and the current, the charge and the current in our RC circuit. So this dq dt actually that is represented here on the first term is the current that is passing through in our circuit, specifically in our RC circuit. So if you're going to ask me now, for now, you have these three equations to recall and use whenever you're provided with an RL circuit and an RC circuit. Now, before I move on with the sample problems, I'd like to ask a question. What have you noticed with the type of first order differential equation here for our model, mathematical model for our RC and RL circuits? What type of first order differential equations are you given here?
Linear, yes.
Linear.
Correct. Very good. So it's linear. So then, having said that it's linear, then you have to recall that when we talk about linear DE class, and I would like to emphasize this, the tool that you are not to forget is that 100% of the time, you always look for the integrating factor. The reason why your model DE was written already and shared in this form, that way you can pick out right away what is your P of T and what is your Q of T. Take note, I'm not saying Q of X or P of X because X is not this time our independent variable, but rather T. Time is our independent variable. In that sense, then, this in your RL circuit, your R over L is your P of T. Then in your E over L on the right side, I like to write it here. E over L is your Q of T. And we know that our integrating factor for a linear D is, I'd like to write it here. Our integrating factor is E raised to the integral. In this case, that would be not P of X, P of T dt. Okay? Now in here, if you have an RC circuit, your P of T this time is 1 over RC. So actually, this is all constants. So resistance and capacitance. In here, this is also a constant, resistance and inductance. Okay, your Q of T then is E over R. So this one is for the RL circuit. This one is for the RC circuit. You deal with it using the technique in finding or evaluating a first order linear differential equations. Okay? Any question? No question? Clear? Okay,
Yes.
Sige, I will clear all drawings here and we proceed to the sample. I will share this one later after the class and I will add more sample problems, documents in the form of documents that you can read later on in preparation for your quiz tomorrow. Okay, so we start here with the source-free RL circuit. So this is our first sample problem. If you look intently in our source-free RL circuit class, the term source-free, what is its implication to you? Source-free, ano siya? It's source-free. What's your understanding of that? Source-free RL circuit. Okay, somebody wrote in the chat, no power source. Correct. Thank you for that question. So no voltage source, no power source. Correct. Okay, in that case now, you have here your inductor and you have here your resistor. Now, I missed to mention it in the model DE that I presented to you a while ago, that our basis for that is Kirchhoff's voltage law. So we sum up the voltage drop across our circuit element in a particular circuit. So that's what we call as the Kirchhoff's voltage law, the voltage drop across each of your circuit elements. So in this case, since we are given an RL and an RC circuit, no, this is an RL circuit only, then we will sum up all the voltage drop across our circuit elements. So we have one here for the inductor and we have one here for the resistor. Since it's a source-free circuit, we don't have any voltage here, voltage source, so it's equated to 0. If it's not source-free, then we have to add here on the left side our voltage for the circuit. So I have, and I think an example wherein it's not source free. Okay, in this case, this is our main equation. But as to the model differential equation, this is our model differential equation. A while ago, let me close this one. I clear the markings. A while ago, I shared that the voltage drop the voltage drop, yes, across your inductor is given by the product of its inductance and the rate of change of current with respect to time. So L di dt. So I will go back so you will here. Here, the voltage drop across our inductor is L di dt. So we place it in here. And then the voltage drop across our resistor, I'm sure you know this very well. I shared it also a while ago. This is the IR, or here R times I. So we place it also in here. Okay, so this is I wrote here a separable differential equation. You may wonder why Miss Alice separable, wherein a few minutes ago you said that the DE, usually the model DE is linear. It's linear class whenever this E here has a value. Okay, if it has a value, especially if this E is an expression which is the sine or cosine function in terms of the independent variable time. If this is a zero class, your linear DE is converted into a separable differential equation. I think you will notice that this is really separable because I'll show to you. Although you can treat this as linear if you want, but it's just like you're still solving it as a separable differential equation. So this is actually separable because you notice that I have here the current I and this dt in here. So I'd like to separate my derivative. So in that case, this particular dE now could be written as dI dt. And I'd like to transfer this one on the other side, and I will have R over L times I. Now this is I. So I can crisscross. I place the I in here. I place the dt in here. So I will have something like di over I is equal to negative of R over L rather dt. So see, it's separable. Why is it separable? This is because this is integrable. This will yield an ln of I. And this one, you have here constants, the resistance and the inductance. So these are constants. So this will just be negative R over L T. If you're going to integrate dt, that would be T plus the arbitrary constant of integration C. However, class, if when you process these integrals, these two integrals, you already place in the limits, like I place here initial current, or it could be capital I, and you have current I at time t, and this is 0 time, and this is a time t, then there's no need for this. There's no need for the C. But if you don't place in the limits in here, then there's a need for you to write in the C here on the right side and determine its value based on the initial condition that is given in the problem. Now, what is the initial condition that is given in the problem? So the problem may give you the initial current. So then all you have to do is substitute that current value in here. And of course, that would be, since it's initial current, the time that we're talking of is 0 time. And of course, if you do that, you place here I value, and this is 0, so you get the value of the C. Now, if you look closely in here on the other side, this is how we do it. Then, if you're just simply dealing with a differential equation which is not related to circuit applications. But now, since we're talking about circuit application and we know that C is representing capacitance, Okay, so it's representing capacitance. It is better, class, that you represent the C as K or any letter that you want, as long as it's not C, because you may get confused or you may forget that this C actually is not capacitance but a constant of integration. So, dire ang gingamit ko, gimbutang ko letter K. That way, you will not misinterpret it as your capacitance later on. Okay? So, note that K is used instead of the usual C because the latter, the C, represents capacitance now. So, if you were just talking about an ordinary TE which has nothing to do with circuit applications, you may use the C. So, this is our DE now. So if you will evaluate our DE using separation of variables, just like what I have written here, you have ln of I plus R over LT equal to ln of K. Now, another question may arise in your minds now, why ln of K? Because I suggested it then that whenever you just have one term in your DE resulting to an ln expression, the constant of integration can be represented as an ln of that constant. Not just a C or not just a K, but an ln of K. Whenever you choose your answer later on, it doesn't matter because both nonetheless will be acceptable. Whether you presented it as ln of K or you simply presented this as K, it's all acceptable. Okay, before I roll down, do you have any question here in this area? So no question for now. Sige, I will clear my markings here. So we go down. So this is our ln, ln I plus R over L times T equal to ln K. Your ln K was transferred on the left and this one was transferred on the right, resulting to this expression. And then further, you have combined here the I and the K in one ln expression using the property of the ln that whenever you subtract, that would be the same as the arguments of the ln's being divided. Okay, so you have now I over K and you have this one. And if you want to eliminate the ln and have a formula, an expression that will solve for the current in your RL circuit at any time t, then you may raise both sides of your equation to E. Or rather, you make this as the argument of the E. If you do that, you will be left with an I over K on the left side, and you have an E raised to negative R over L times T on the right. Now then, transferring the K on the other side, this is now your finished working equation for an RL circuit. Given the time, given the R and the L, the resistance and the inductors, and having determined the K initially, then you'll be able to determine the current I that is passing through your circuit, that is passing through your circuit elements. This formula is called the natural or transient response of the RL circuit. So if the problem will be asking you what is the natural or transient response of an RL circuit having this resistance, having this inductance, having this after this particular time, then this is the formula to use. Now question, Miss Ali, do we need to go back to our model DE here? That way everything is shown when we solve? The answer is no. You can use this particular formula right away when you solve for your whatever it is that the problem is asking, as long as your original DE, this original DE will work for what is being required. So if you are asked for the current, then why go back to this one? Because anyway, you have already the formula in your disposal. So this is pre-derived for you already. Just like when we had growth and decay, when we have Newton's law of cooling, we didn't go back to the original DE, but we made use of the formulas that we have derived already. So since this is derived for you, you can use this right away. Now, all you have to do is substitute. So it says here, substitute the given initial conditions, time equal to 0, and I equal to IO if the problem gives you specifically the IO. That is may number, gid siya bala class, may ginhatag, gid siya nga 10 amperes is the initial current or 2.5 amperes is the initial current. If it's not specifically given, you can simply represent the I, the current, as IO. In that case, class, since we want to replace this constant here, K, by a specific value, then we substitute this initial condition. Again, I will emphasize, if IO has a specific value, then it should be the specific value that you will use. If not, then you just simply write IO here, then equal to K here, then you have E raised to 0. The time here is 0 because we're substituting the initial current passing through our circuit. So if you could see now, E raised to 0 is 1. It follows, class, that the K that you are seeing here, is actually your IO. Okay, because this is 1 times K, so that will be K, and K is equal to I sub O. Now you can now replace your K by IO. Okay? So this one, this highlighted formula is more specific than the one that is provided here on top because all you have to do, class, is just plug in the initial current that is given by the problem. And then whatever is the given resistance and inductance, you also substitute it in here. Given the time, you will be able to determine the natural or transient response of your circuit. Okay, so this is your ready-made current. And this is the current in your circuit at any time greater than 0. That is when the circuit is already a closed circuit, when there's a current already passing through all your circuit elements. Okay? Any question here? Any questions so far? Okay, if there's none, I'd like to move down further. You see this curve in here? On the vertical axis, you have the current. On the horizontal axis, you have the time. So you could see that the relationship between current and time is inversely proportional. It is said to be decreasing exponentially. It's decreasing exponentially. Okay, we increase the time, your current decreases because you can see the curve is going down. It should be increasing if it's done like this. It's an exponential increase if it's like that. Let me show to you. Okay, it's an exponential increase if it's like this. Meaning, as time increases, current increases. But in this case, it's the other way around, class. So, as the time increases, current decreases. Okay? And this is the equation. This is the equation of this formula that we have in here that determines the current at any time t for our circuit. Okay? Now, you have this particular tau here. I'll close this one. You have this tau here, the L over R, the reciprocal of the RL that you have here. So what is this tau? This is the time constant. So take note, if you would be asked of this question, it's the time constant of the RL circuit. And what does it represent? It is the time it takes the current to drop to 36.8% of its initial value. Now, let me allow me to speak in our language para maintindihan. Amo ni siya ang time nga pagsugod close ang circuit mo, ang current mo nga gaagi na lang sa circuit mo is 36% of its original amount. If it's depicted, class, in this particular graph, relationship between T and the current, this 0.36 IO, meaning this is 36.8% of the initial current, this is the time it will take that current to drop to this value. From its initial value of IO, it will drop to 36.8% of this value by what time? By tau time. Okay, as defined in here. So that's the essence of the tau. The time it would take for the current, the initial current of your RL circuit to drop to 36.8% of its initial value. Okay? Any question for so far? All clear? Sige.
Yes, miss.
Sige. So if it's clear, I'll go down. I'll go to our sample problem, which this time talks about the inductor. Okay? If the inductor this time has a current IL equal to 2 amperes at time equal to 0, take note, ano na siya? Time equal to 0, meaning this IL that is given here is now IO, and it has a specific value of 2 amperes. So you are to find an expression for I sub L valid for t greater than 0 and its value at time which is equal to 200 microseconds. And this is our resistance and this is our sige, this is our resistance. Suli ako label class. Okay, right. This is our inductance. This is our resistance. Tsakto galing. So this is our resistance in ohms and this is our inductance in millihenries. Okay, so what we do, I will need to clear my markings before I can go down. We just go back to our equation. This is our equation, right? So we will just substitute 2 for the initial current, 200 for the resistance, and you have 0.05 for the inductance. Wait, class, ha? I have a call. This might be important. Just wait. Okay, sorry, but about that class, it's really important actually. So we have now substituted the values here and we substituted it in here. This 200 class is 200 for the time microseconds. So when you speak of micro, that's times 10 raised to negative 6. So you have to write 200 times 10 raised to negative 6 seconds. So the let me just write it here. So then this must be now already having the unit seconds. So if your time, if the provided time in the problem class is not seconds, it's microseconds or milliseconds, you have to really convert that to seconds. So that is why you get here 200 times 10 raised to negative 6. So your current now is 0.8987 amperes, or that would be, if you multiply it by 1,000, that would be 898.7 milliamperes. Why? Because we multiplied it already by 1,000 and converted the amperes to a smaller unit, which is milliamperes. We have 1,000 milliamperes equivalent to 1 ampere.